Moving on, let's talk about electrolytes. So an electrolyte, you've probably heard of this if you're getting sick or you're not, playing sports, something like that. Drink your electrolytes or make sure you're replenishing your electrolytes. Well, what are electrolytes? Well, electrolytes are just something that's going to conduct electricity. So it's going to have to form ions or it will have to have already had ions in solution. So either way, there's going to be ions in solution. Now this is called a dissociation equation. And the term dissociation happens when we have a soluble ionic compound. It puts it in water and it forms the ion. So the ions separate because the positive ion is going to be attracted to the negative dipole on the oxygen. And the negative ion is going to be attracted to the positive end of the dipole on the hydrogen. So they get surrounded by the water molecules and they dissolve. Not everything that dissolves forms ions, but ionic compounds do. And it's called dissociation because they dissociate. They move apart from one another. So they're breaking apart. Dissociation is the term used when we have an ionic compound. Because there are already ions present here, they just break apart. They move away from one another. That's dissociation. So when we put this into, speaking of this beaker here, and we put the electrodes into a substance that is an electrolyte, the light bulb will light up because the electric current is going to flow. So there's a pathway for the electric current to flow through the ions through the solution. However, in a solution that does not form ions, we do not have a pathway. So an electrolyte is something that conducts electricity because it has a pathway for the electric current to flow. So if you're swimming and it's a lightning storm, you shouldn't swim because there are salts dissolved in our water, or also water can do what we call self-ionize. It's not dissociation. We'll talk about the term ionization in a moment, where it can actually ionize itself and you would have ions in the water. So it's not safe to swim. Now, if you were swimming in distilled water, or deionized water, technically you could swim, but again, water can self-ionize, so it would not be safe. A non-electrolyte is something that does not conduct electricity, non-electrolyte. So here we have sugar. This is sucrose. So sucrose, when we put it in water, does not form any ions. This is a covalent compound, so there are no ions. And there are no ions over here on the right. Now, some of our covalent compounds can form ions by doing what's called ionization. And again, we'll talk about that in a minute. But some can form ions. That's an ion. But those are polar covalent, usually. So I will give you some criteria in a moment. The nonpolar covalent, always non-electrolyte. So because the sucrose remains intact in the water, this is water, but because the sucrose stays together, there are no ions, so there is no pathway for the electric current to flow through, so the light bulb does not light up. Now, weak electrolytes, see how the light bulb is lit up but not very strong, means there are some ions in solution, but not a lot. So an ionic compound that's soluble will form a lot of ions in solution. Usually 100% of them will ionize. A weak electrolyte is something that does form ions, but it doesn't form very many. So it produces ions when it dissolves, but it's predominantly still in the molecular form that it was in, and it's not ionized. So weak acids would be like our weak acid, weak acids are also weak electrolytes. So this is carbonic acid. So I'm going to write this out. H2CO3 would go to H plus HCO3 minus. So we can see that forming the ions. Now this is carbonic acid, goes with that one. This is actually acetic acid here in this example. And we form this plus, this should be a minus sign here. So we have H plus and then this. So this H is just coming off. That's the reason why it's written HC2H3O2, is to say that this is actually an acidic hydrogen. So one of the reasons we write it first. Now, I asked you a while back to remember that ammonia is a weak base because it's important. It's one of the only, it's one of the popular organic bases that we have. So NH3, this is showing it reacting with the water. So it's reacting with the water to form ions. So we get the hydrogen goes here, so we have HOH, remember? So the H goes there, and then the OH is left over. So if you were to buy ammonia, you're technically buying ammonium hydroxide, and it's going to be in solution with itself. So this is a weak base. We form some of these ions in solution. There's very few, so if you notice, a lot of it is still intact in its molecular form, and there are some ions present. So while there is a pathway for the electric current to flow, there are not a lot of ions, so it doesn't flow easily. Strong electrolytes are going to be something that dissolves completely. So ionic compounds that are soluble, so soluble ionic compounds, highly polar compounds, because we went over polarity. So these are just examples of soluble ionic compounds here. I'm going to get the solubility chart out in a moment and show you how to figure that out. There are 7 strong acids. It's easy if you memorize them. So HI, hydroiodic, HCl, hydrochloric acid, HBr, hydrobromic acid, HNO3 is nitric acid, H2SO4 is sulfuric acid, HClO3 and HClO4 we have chloric acid and perchloric acid. Now strong bases would be like sodium hydroxide, potassium hydroxide, calcium hydroxide. So anything in group 1 or group 2 metal hydroxides. So iron 3 hydroxide would still be a base, but it's a weak base. So group 1 and group 2 metal hydroxides are always going to be strong bases. So it's best if you can memorize those 7 strong acids and these strong bases that are group 1 and group 2 hydroxides. That will help you. And then I'm going to show you how to determine this with the solubility chart. This is a table from the book. It just shows you these are ionization equations. Ionization happens when ions were not present to begin with. So dissociation, we had ions to start, and they move apart. They separate. Ionization is what happens when we have a covalent compound that forms ions. These are ionic compounds. So a covalent compound doesn't have ions to begin with. It's not ionic. There are no ions. But it can react with water. So if you were to say HCl plus H2O, you would see H3O plus Cl minus. But this is just a shorthand for this, so we can actually put water above the arrow either way here, and saying that the H plus would be the H3O plus. So when we talk about acids and bases, the concentration of H3O plus determines the acidity. We actually use that interchangeably with H plus concentration, so we do use those interchangeably. So these are both the same type of reaction. Notice that each hydrogen is going to be lost stepwise. So in something that is diprotic, like H2SO4, this is the strongest reaction and produces the most ions in solution, but it can lose both hydrogens and produce SO4 2-. But that one, you can notice, is a double barbed arrow, means it goes back and forth. Everything else is a single arrow that goes one direction because that's the way that it's going to produce the most ions. So you should know those 7 strong acids, just going to make your life easier. Soluble ionic compounds are those that dissociate completely. So 100% of the ionic compounds become ions. That gives a very large, so they're strong electrolytes. Gives a great pathway for the electric current to flow. We're able to write a dissociation equation and then determine the concentration of the ions that are produced in a solution by just looking at what the concentration of our initial compound was, so our initial ionic compound. Now this is important, especially if we're doing colligative properties that I mentioned in the last video. We're not doing them in this semester, but you will if you take another chemistry course. Those are going to talk about how many ions are in solution, and it's going to multiply the effect. So it is important to be able to determine that. We do that by just using mole ratios. So we can calculate the concentration of all species. So species, if I were to say, just pick a compound, so K2CO3, if this were to dissociate, I'll write the dissociation equation, I would form 2 potassium ions and 1 CO3 2- ion. So the mole ratios tell me for every one of these that dissolve, I get 2 potassium ions and 1 carbonate ion. So we can use this. So if I were to say I had 0.5 molar here, what would the molarity of this be? We're talking about moles per liter. I would just multiply by the mole ratio. So there'd be 2 times the amount of potassium ions, because every time one of these dissolves, I get twice the amount of potassium ions. And there would be the same one. So this would be 1.0 molar potassium ions, and this would be 0.5. Now we're going to go through the math, and I'll show you how that works. But I just wanted to say, in general, it should be intuitive, and we multiply by the mole ratios. So what would NaCl dissociate into? So we're talking about NaCl breaks down into how many sodium ions and how many chloride ions. So it would be 1 Na and 1 Cl anion. So 1 sodium ion and 1 chloride ion. What about Na2SO4? Pause it, try it. 2 sodium ions and 1 sulfate anion. And aluminum chloride, 1 aluminum and 3 chloride. So we're just looking at those ratios for these, and then we're going to do a little bit of math. These are dissociation equations, so Na2SO4, there are 2 sodium ions, so we have a 2 here, and there's 1 sulfate, so we have a 1 there. FeBr3, we have a 1 for iron, and we have 3 Br-. Remember, we still need to be able to figure out what the charges are and put those in, but notice we're going from a solid to an aqueous solution in all cases here. If this is an insoluble ionic compound, this would not happen. So if it's insoluble, you would put no reaction or something like that. So find the concentration of all species in a 0.25 molar solution of magnesium chloride. So if this is all that you were given, you would need to write the dissociation equation. So magnesium chloride solid goes to magnesium ions, 1 of them, and 2 chloride ions. Now we say this is 0.25 molar. Okay, we would like to know what is the molarity of magnesium ions and what is the molarity of chloride. Now if you get it, you can totally just multiply by the mole ratio, but if not, let's set it up. So 0.25 moles of magnesium chloride divided by 1 liter. This is what I just wrote. It's just expanded because molarity equals moles divided by liters. So I want to get rid of magnesium chloride and go to magnesium ions. So I can say for every 1 mole of magnesium chloride, I have 1 mole of magnesium ions. And now I'm in magnesium ions over liters, so this would be 0.25 molar Mg2+. For chloride, 0.25 moles of magnesium chloride over 1 liter. For every 1 mole of magnesium chloride, I get 2 moles of chloride anions. So this would be 0.50 molar Cl minus. So when we do this, generally I will ask you to write the answer in square bracket notation. So the concentration of magnesium ions is 0.25 molar. The concentration of chloride anions is 0.50 molar. So that is square bracket notation. I wrote the concentration. Notice there is no 2 in the chloride because I took that into account here. I don't write the coefficients in the square bracket notation. All right, I would like you to try these, so please pause the video and try it, and then I will go through them with you. But you got to pause it and try it. This one is a little bit more difficult. I did not give you the dissociation equation, so you should look them up and, write the dissociation equation. Using the square bracket notation, express the molar concentrations for all species in the following solutions. So barium hydroxide is a solid. We put it in water, and it's going to produce 1 Ba2 plus ion plus 2 hydroxide anions. NH4Cl as a solid, put it in water, and you get 1 ammonium aqueous plus a chloride anion. The first one says we have a 0.42 molar solution of barium hydroxide. We would like to know what the molarity of both of the anions are. And here we have a 1.2 molar solution. We would like to know the concentration of both of the anions. So barium hydroxide, we have 0.42 moles of BaOH2 for 1 liter. For every 1 mole of barium hydroxide that dissociates, we get 1 mole of barium ions. So this will be 0.42 molar Ba2 plus. And down here we have then 0.42 moles of barium hydroxide for every 1 liter. And for every 1 mole of barium hydroxide, we get 2 moles of OH, hydroxide. So this will be 0.84 molar OH. It says square bracket notation, so the concentration of barium ions here is 0.42 molar, and the concentration of hydroxide ions is 0.84 molar. Here we have 1.2 molar ammonium chloride. Now I'm going to do what I've been doing here and write moles over 1 liter. So for every 1 mole of ammonium chloride that reacts, we get 1 mole of ammonium ions. So 1.2 molar NH4 plus. Yep, running out of room. I'm going to go over here, 1.2 moles of NH4 plus, NH4Cl, divided by 1 liter. For every 1 mole of ammonium chloride, we get 1 mole of chloride. So 1.2 molar N8, getting ahead of myself here, chloride anions. So the answer in square bracket notation would be the concentration of ammonium ions is 1.2 molar, and the concentration of chloride anions would be 1.2 molar. There we go. There are some terms that go along with solution, so we're going to talk about solubility here in a minute. When we dissolve something in a solution, it can be saturated, unsaturated, or supersaturated. Saturated solution means the concentration is at the maximum amount that will dissolve. So if I'm putting sugar into Kool-Aid, there's a point at which the sugar stops to dissolve and it just sinks to the bottom and no more will dissolve. That is saturated solution. So the sugar just continually goes to the bottom. If you add any more, that's saturated. So no more can dissolve. Unsaturated is before you hit that maximum, you're adding sugar to the Kool-Aid and it continually dissolves. You might have to stir it, but it will keep dissolving. That's unsaturated. There's room to dissolve more in the solution. Supersaturated is a special circumstance that is very unstable. It's very unstable. So if you were to make a supersaturated solution and then you maybe sneezed on it or moved it wrong, everything could come crashing out of solution very quickly. So what we can do is we can make a saturated solution and then we heat it up and we dissolve the rest of that substance that was on the bottom of the flask or beaker or whatever. We dissolve that into the solution and then we filter it to get out anything that might be left in there and then slowly let it cool. And normally it will all stay in the solution, even though there's more dissolved in there than what should be able to be dissolved. So if we can only dissolve 50 grams at room temperature and then we heat it up and the rest of it dissolves, maybe there's 60 grams dissolved instead of 50. But if you drop just one tiny piece into the beaker, all of it will come crashing out of solution. So it's pretty cool. I'll try to link a video that you can see the picture of it or the video of it. It's pretty neat. So how do you tell the difference? If I had 3 beakers on the counter, how do I tell the difference? So which one is saturated, which one is unsaturated, which one's supersaturated? I would add 1 piece of the solute. Add a tiny amount of solute. If it's saturated, it will sink to the bottom. If it's unsaturated, it will dissolve. And if it's supersaturated, the whole solution will crystallize. And all of it will come crashing out of solution. It's pretty cool to watch. Miscible and immiscible. Miscible means that the liquids dissolve in each other in all proportions. So that'd be like alcohol and water. So you don't want somebody to know that you're drinking their alcohol. You put water in it. Until they taste it, they're probably not going to know because they're miscible. You're not going to be able to tell that you've dissolved one in the other. Immiscible would be something like oil and water. They are not going to be soluble in one another. So if you use dressing or something like that, you always have to shake it before you use it because they are not soluble in one another and they're going to constantly be falling out of solution. So solubility for a substance is determined by temperature as well as how much solvent. So when you say there are 100 grams of sodium chloride is soluble in, actually let me change that because I don't think that's anywhere near. let's say 58 grams of sodium chloride is soluble in 100 grams of water at 25 degrees Celsius. So I must have the amount of water and I must also have a temperature because those are important. If I were to double the water, I should be doubling the solubility, and if I change the temperature, the solubility will also change. So as you see, as temperature increases, solubility increases. Now with sodium chloride, it's not that big of a slope here. We see it gently increasing, but potassium nitrate increases exponentially as we increase the temperature. So depending on what we're trying to dissolve, solubility will definitely increase with temperature, but not sure how much. And that's not every substance, but that's most substances. So what are the solubility rules? So the solubility rules is a compound is soluble if it contains one of the following cations. This one you need to know for the final. You have to have that memorized. A compound is soluble if it contains one of the following anions. You should also know this one. So anything in group 1 or with ammonium is always soluble. In fact, we put things with those just to make them soluble when something is insoluble. Because these are small, most of these are going to be soluble. Now, unless they're with one of these 3 cations. Nitrates, chlorates, perchlorates, acetates, sulfates, they're all, sulfates are sometimes, but acetates, nitrates, there are no exceptions to those. They're always soluble. Now, strontium, barium, mercury 1, and lead 2, those are going to be insoluble with sulfates. Now, I have a better chart that I like to look at. This is what you have available to you on Blackboard. So these are the soluble compounds. So anything in this list is soluble unless it is combined with one of these. Now you're going to notice that all of these are anions. This is the only one that's cations. So if these are anions, these are all going to be cations. So if we have this anion combined with lead 2, it's going to be insoluble because it's an exception. Normally they're soluble, but an exception makes it insoluble. And now this would be the bottom of this page if you print it. These are insoluble compounds, so these are all insoluble anions. Normally, unless they're combined here, if they're combined here, they are soluble. Use it, double check your answers a couple times, you'll get it. There are going to be like the first couple rules that you do need to know. So we're going to go through these. I want you to pause it and try to classify these as an electrolyte, a non-electrolyte, or a weak electrolyte, or a strong electrolyte. So go ahead and give that a try. Pause it and try it. Citric acid. It is not one of the 7 strong acids you needed to memorize. But it is still an acid, so that means it would be a weak electrolyte. Potassium phosphate, I'm going to go back. Phosphate is here. It's normally insoluble, but since it's an alkali metal cation, potassium is an alkali metal cation, it is soluble. So this would be a soluble ionic compound. So it would be a strong electrolyte. Glucose. C6H12O6, by now I would expect you to say that this is a non-electrolyte. So this is a non-electrolyte, so this would be, nonpolar. Yeah, okay. So this is a non-electrolyte. It's covalent, not highly polar. Well, not going to conduct electricity. So precipitation reactions, this was your metathesis reactions lab. So if you haven't done that yet, you'll still get the benefits of this. Most of you probably got it. It's pretty self-explanatory, but just in case, let's go through it. So precipitation reactions. We have a couple different types of reactions that are considered intermetathesis reactions. Precipitation reactions where we have a insoluble product. So an insoluble product would be anything that is not aqueous. So that would be a gas, a solid, or even a liquid like water. So we're going to have to be able to use that solubility chart and determine whether things are soluble. Typical precipitation reactions have both reactants are soluble and then an insoluble product. So here, remember we have cation A, anion B, cation C, and anion D. So here we have CD and AB. It doesn't matter which order you put them in. It could be AB and CD. But here we have K plus and NO3 minus. That gives us KNO3. And here we have A is PB. So here we have PB2 plus, NO3 minus. So we have PB2 plus and I minus, giving us PBI2. So the reason I'm writing those out is just to remind you where we're getting those, because you'll probably have to predict the products for these type of reactions. There's also acid-base neutralization reactions. These are non-electrolyte forming, so we form a water compound. Remember, water can't be aqueous, it is liquid, because water can be a solid, a gas, or a liquid, but it can't be dissolved in water. So aqueous means dissolved in water. So water can't be dissolved in water, so this is a liquid. So this would be our insoluble product. So cation A, anion B, cation C, anion D forms AD plus CB. Oxidation redox reactions, we're going to talk about those in the next video, but we have a single replacement. So the magnesium is going to replace the hydrogen to produce magnesium chloride and hydrogen gas. So we're going to talk about these in depth and how to balance these equations, which is a lot harder than any of the balancing equations we've done so far. So this is the molecular equation. We've been writing these all along. So we have cation A, anion B, cation C, anion D forming CD and AB. We predict the products. We figure out which is insoluble product. And we don't forget to balance it. So you have to predict the products first, balance it, and then figure out which is insoluble and write your state symbols in for all of these. Now remember, your reactants should be aqueous, but you should always check them just in case. So these are the complete formulas. But what we do in these type of reactions, these net ionic equations, is we see what's really important. So right now you might actually be looking for cooking reasons. What can I substitute? Because you don't want to go to the store. So nobody wants to go to the store right now. So what can I substitute? What can I change? Same for chemists. So sometimes we don't have, if I don't have potassium iodide, can I use something else? Well, since potassium is not really involved in the solid product, I could use sodium iodide and it would be the same result. I would still get what I need and it would still have a soluble product on the other side. So this is going to tell us what is really important and what we really need. So this is the first step, is the molecular equation. Predict the products, balance it, and then figure out which is insoluble product and write your solubility in there. Wrong way. The ionic equation, I'm going to try to do a screen thing here. So All right, so I'm pretty sure that was our formula, excuse me, our equation. So the ionic equation, the complete we separate all aqueous substances into their ions. Because when we put this into a beaker or a reaction vessel, they're going to separate into their ions. So they're all going to be just floating around as ions. So looking at PbNO3, 2, I have one lead ion. This is aqueous, so I'm going to separate it out. I'm going to say I have one Pb2+, and it's aqueous. So this is dissociating. Okay, the NO3, I have two NO3 minuses. How do I know that? Because there's a 2 here, and the 2 comes up and becomes a coefficient for the anion, and that is also aqueous. The next one, I have 2 potassium ions, which are aqueous, plus I have 2 iodide anions. That is my reactant side. On the product side, I have 2 potassium ions, plus 2 nitrate anions, plus my PbI2. And why did this one stays together? Because it's a solid. It is not aqueous. So because it's a solid or it's an insoluble product, it stays together. The next thing to do is look for the spectator ions. Just very simply, spectator ions are the same on both sides. So NO3 and NO3, I have 2 of them. They're both on the same side. That would be a spectator ion. The potassium, those are spectators. Now these ones are not spectators because they go into making the solid. So since those go into making the insoluble product, they are not spectator ions. So what we then do for the net ionic equation is whatever is not used in, or excuse me, whatever goes into making this insoluble product is our net ionic equation. So basically anything that's not circled goes into the net ionic equation. So Pb2 plus 2I minus PbI2 solid. So that is our net ionic equation. This is what we must have. We must have a lead 2+ compound, 2 iodide, and anything else. So we could use, as a cation, I could use potassium because it's soluble. I could use sodium. I could use strontium. I could use calcium. I could use a lot of different options here. Now for the lead, I have to have some type of soluble anion. So it could be a nitrate like we have. It could be an acetate. And you know, there's a couple other options that we could use. So basically anything that's soluble in the product can be used in place of something if we don't have it. So these are the spectator ions in the PowerPoint. They're circled. Now a lot of times you'll see people cross them off. So crossing them off. Now I'm not sure how we're going to do this. I'll probably just have you identify them because it's going to be a multiple choice test on Blackboard, but usually when I'm grading these by hand, I don't want you to cross them off because then I can't read them. So that's why I have you circle them. And then if we were crossing them off, it would be anything that's not crossed off is going to be your net ionic equation. So here's our net ionic equation, and we only show the ions that undergo change. So I want you to write the molecular, the ionic, and the net ionic equations for this reaction between silver nitrate, which is soluble, it's a nitrate, and sodium carbonate. Well, sodium, so it's soluble. Please pause it and try it. So what we need to do first is predict the products. Cation A, anion B, cation C, anion D. So we're going to get AD plus CB. So A is silver and D is carbonate. C is sodium ion and B is nitrate. So we cross these down and we get Ag2CO3. And here we get NaNO3. Now we need to balance it. So let's see, we have 2 silvers. So that gives us 2 Ag, 2 NO3, 2 sodium, and 1 carbonate. Here we have 2 Ag, we have 1 NO3, 1 Na, and 1 carbonate. So if we put a 2 here, 2, 2, and now we're balanced. So now we need state symbols. So if we look at our solubility chart, we're going to find that silver is going to be our insoluble product here. And our sodium nitrate is going to be soluble because all nitrates are, I wrote solid. And our sodium nitrate is going to be soluble because all nitrates are soluble. So now we have the molecular and it's balanced. So that's step 1. The ionic equation, we separate all AQ. So this is our complete ionic. This is molecular. So we have 2 silver ions plus 2 nitrate ions plus 2 sodium ions plus 2, oh, just kidding, just 1, getting ahead of myself, plus 1 carbonate anion. Over here, this is a solid, so it stays together, Ag2CO3, solid, plus 2 sodium ions, plus 2 nitrate ions. We're going to circle the spectator ions. Silver goes into the solid, so no. Nitrate, nitrate, sodium, sodium, carbonate goes into here, so we're good. So our net ionic equation everything that's left, 2Ag plus aqueous plus CO3 2 minus goes to Ag2CO3. All done. And try again. So again, pause it and try this if you haven't already done that. You want to make sure you're doing that. CaNO3 2 plus rubidium phosphate. So we get, let's see, A, B, C, D. So A, D, C, B. AD would be Ca2 plus, and D is PO4 3 minus. And CB would be RB plus, and B is NO3 minus. So we're going to crisscross those down, and I get Ca3PO4 2. And that's going to be solid if we look at our solubility chart. And here I get rubidium nitrate. Both are soluble, so that would be AQ, as rubidium is group 1 and nitrates are all soluble. So we need to balance this. I have 1 Ca, 2 NO3, 3 rubidium, and 1 PO4. Over here I have 3 Ca, I have 1 NO3, I have 1 rubidium, and I have 2 phosphate. So let's see, I need a 3 here, that makes that a 3, that makes this a 6. Then I have my nitrate, so I'll put a 6 here, I get 6 and 6. So here I would need a 2, and that becomes a 6 and a 2. And now we're balanced. So erase that. That is our balanced molecular equation. Now the complete ionic, we separate everything that is AQ. So I have 3 Ca2 plus aqueous plus 6 NO3 minus plus 6 Rb plus 2 PO4 3 minus. This stays together, Ca3 PO4 2 plus 6 Rb plus 6 NO3 minus. Spectator ions, we're going to circle those. So our spectator ions are nitrate. There are 6 of each, that's good. And rubidium. Make sure there's the same number of both on each side. That means you balanced it correctly. And then we do our net ionic equation. So whatever's left over, 3Ca2 plus 2 PO4 3 minus is Ca3 PO4 2 solid. Just keep practicing them. We got to look at the solubility chart to see which is soluble, which is insoluble. That's what we're doing here, just figuring out what we could use in place of something else. So now we're going to talk about acid and base. We're going to basically talk about conjugate acid-base theory, which is based off of the Bronsted-Lowry. So the Bronsted-Lowry theory. And this is probably the easiest definition of acids and bases and the one that most people remember. Now I will mention what an Arrhenius acid-base is and a Lewis acid-base definition, but this is the one we're going to focus on, and this is what allows us to do conjugate acid-base theory. So let's just go over some properties of acids. Acids are going to be our aqueous solutions of acids. They have sour taste. So if you have ever eaten citrus fruits and they have a sour taste, that's citric acid that you're tasting. You should never taste an acid in lab, even though it should have a sour taste as well. When we use litmus paper in lab, litmus paper should turn red when it's dipped into an acid. Well, we've gone over this before. Whenever we react a metal with any acid, it should produce hydrogen gas. And I know that we've gone over that, but this is where we should start putting that into practice. It may not always be given and told that it's a byproduct. We should know that because it's being reacted with an acid. So when reacted with a base, in this case, it's actually going to produce water and a salt. So remember, a salt has a definition of the cation from a base and the anion from an acid. So salt is not just table salt, sodium chloride, but a salt is something that is formed whenever the cation from an acid and the cation from a base and the anion from an acid get together. They are conductors of electric current and heat. So they are good conductors, whether they are, I should say they are conductors. They're not always good. They're good if they're a strong acid, but if they're a weak acid, they will conduct a small amount of electrical current. So there are two different types of acids. We mentioned this briefly during the naming lab, but we're going to go over it again really quick. We have a binary acid and an oxyacid. Binary acids are going to contain only two different types of elements. Hydrogen is always one of those elements, and then one more element. That element is generally more electronegative than was one of the more electronegative elements. So it's definitely more electronegative than hydrogen. So how do we name binary acids? We did go over this during the naming lab, but we always begin it with hydro. The root is the second word, so the second element. You take the root of that name, you drop the ending and add ic, and then acid. So HCl would be hydro, for saying that it has the hydrogen. Chlorine, we drop the ending and say chloric acid. Hydrosulfuric acid. So these are ones that we have done. I'm hoping this is review. Okay, oxyacids. Oxyacids, we have hydrogen, oxygen, and one other element. That's usually a nonmetal. So how do we name these? We take the most, well, usually those are our polyatomic ions. And we are going to take the name of the polyatomic ion and we're going to change the ending. Remember, most of our polyatomic ions end in ate or they end in ite. And those are what's going to determine which the ending of our acid is. So if the polyatomic ion ends in ite, we change it to ose. So H3PO3, this is phosphite here, so it would become phosphorus acid. So this was phosphite, so it becomes phosphorus acid. If it ends in ate, we change the ending to ic. So here we have nitrate, that becomes nitric acid. There we go. Now if we had HNO2, this would be nitrite, we would get nitrous acid. The 5 common acids that you probably will interact with most in your life. Sulfuric acid, you use it every day. You drive your car, you may not know that, but this is battery acid. And it's most commonly produced in industry, so we use this a lot. It's also used to manufacture fertilizer, dyes, detergents. It's used quite a bit in our life. Nitric acid is going to stain proteins yellow. It's also used in making explosives, but there are a few other uses for nitric acid as well. So we might use that a lot in our biochem lab. Phosphoric acid is used for manufacturing fertilizers, animal feeds, used in detergents and ceramics. It is going to be used in animal feeds definitely as a preservative. Hydrochloric acid, this is your stomach acid, so stomach acid. So we use that in digestion. It's also used to pickle iron and steel to harden them, and it's used to maintain acidity in swimming pools. So you can use hydrochloric acid to make sure your swimming pool is the right pH. It's not the only one that's used, though. We can use muriatic acid or other things. Acetic acid is white vinegar. This is something that we use. So vinegar that we get is commercially available as 4 to 6% acetic acid. But you can get cleaning vinegar, which does generally kill a lot of germs, but I'm not going to comment on how vinegar reacts with COVID-19 because I don't know. You can get 35%. So glacial acetic acid is what it comes in, where it's like kind of the most pure acetic acid we can get, and then we dilute it down. So when you buy vinegar from the store, you're buying 4 to 6% acetic acid. Bases taste bitter, and they also feel very slippery. So bases are going to change litmus paper to blue, and they feel slippery. Like if you're in lab and you feel like your hands, you could just put soap on them, you definitely want to wash your hands if you didn't put soap on it, because you probably got a base on your hands. They react with acids to form salt and water. So remember, this is a salt is the cation from a base and the anion from an acid. They also conduct electrical current. If they're strong, they'll do so strongly, and if they're weak, they'll do so weakly. So Arrhenius acids and bases we're talking about the concentration of H3O+. So when we talk about pH and calculating the strength of an acid or a base, we're going to be talking about the concentration of H3O+ in solution. Remember, I said we can kind of use that interchangeably with H+ or hydrogen ions. So Arrhenius acid. So an Arrhenius acid is a chemical compound that increases the concentration of H3O+, hydronium ions, in aqueous solution. Because it says that acids ionize in solution, they react with the water, and the water then produces, when you add a hydrogen to water, you produce a hydronium ion. So Arrhenius base then is going to increase the concentration of hydroxide ions in solution. So bases, in that case, increase OH minus. A strong acid completely ionizes an aqueous solution. So it ionizes 100%. Notice it doesn't say dissociate. It ionizes because these come from our covalent compounds. So they react with water. So strong acids are going to be strong electrolytes. They're going to ionize 100%. They're going to have a lot of ions for the electric current to flow through. The reaction equation shows a single arrow to the right for all except the second hydrogen that gets lost from H2SO4. These are the same 7 strong acids that I gave you that you should probably memorize. Now, a weak acid is going to release only a few hydrogens in solution. So organic acids are usually going to be weak acids, and they're represented with a double arrow to say that they don't all go forward. So anything like this means it's strong. If you see something like this, it usually means it's weak and it can go forward or backwards. How strong is a base? Well, it depends on which extent it dissociates to. So strong bases are also strong electrolytes. Most of our compounds that contain nitrogen are weak bases. So these would be our organic bases. Strong bases are going to be any alkali or alkaline earth. So this is group 1 or group 2 metal hydroxides, just like we mentioned a few slides ago. Bronsted-Lowry acid bases, this is the one I said that most of you are going to remember. This is also the one that is responsible for conjugate acid-base theory. So Bronsted-Lowry acid is a molecule that is a proton donor. So a proton donor is going to be able to donate a proton, a hydrogen ion. All acids are going to donate protons to water. So if we see here, this hydrogen gets donated to water to form H3O plus and Cl minus. So if you notice here, this is also increasing the concentration of H3O plus ions. So it technically is the similar definition to the Arrhenius acid. Water can self-ionize. It can react with itself to form the hydronium ion as well. A base, a Bronsted-Lowry base, is a proton acceptor. So it accepts the proton from the acid. Water can act as a Bronsted-Lowry acid or base. It's known as amphoteric. It can act as an acid or a base. So Bronsted-Lowry bases can be made from molecules or from ions, in this case KOH with water. Now normally we don't put water as a reactant, we put it above the arrow with bases. That's just a thing. So we would write KOH. And we don't even necessarily have to put water there, but it'd be OH minus plus K plus. Just otherwise it doesn't really work out so well. We have to think about it too much. There are different types of acids. Monoprotic, meaning it can only donate one hydrogen, and polyprotic, because we can have diprotic and triprotic acids. So monoprotic, we only have one hydrogen here, here, and here, meaning they can only donate one hydrogen. So if we look then at our we have monoprotic. Let me just start this slide over. Some acids can donate more than one hydrogen. So we have monoprotic acids that only have one hydrogen to donate. So when they donate their hydrogen, that's it. They don't have any more. They can't donate anymore. But then we have polyprotic, where we can have a diprotic, like sulfuric acid, that can donate 2. Or we have triprotic, like phosphoric acid, that can donate 3 hydrogens. But the first one, the first ionization, is always going to produce the most ions, and it's going to happen the quickest. So polyprotic, and then we have within polyprotic, poly meaning many, we can have diprotic or triprotic. Now we always ionize one hydrogen at a time. So sulfuric acid would lose one hydrogen, right? So we go, this hydrogen goes here to water, we get H3O plus and HSO4 minus. Notice this is a strong reaction. going in one direction. But now this can react to lose its hydrogen as well. The HSO4 loses its hydrogen here to water to become H3O+, and the SO4 2- has no hydrogen left. But notice this is weak because it has a double barbed arrow. They always happen in stages. This one is always going to produce the most ions, is the first step. The first step always produces the most ions because it's strong. This is a strong acid. This is a weak acid, so it will produce less ions. This is just the strength of some common acids and bases. Feel free to take a look at it. It's from your book, and that's just something for you to peruse, I guess. So there are two types of polyprotic acids, diprotic and triprotic. So diprotic is a two-step process because it can lose two hydrogens. So here we have sulfuric acid again, two-step process. Triprotic means it should happen in a three-step process because it can happen and it can lose three hydrogens. So a three-step process would be here. This is the strongest one. So strongest produces most ions. We get then this one that can lose up to two. So we have H2PO4- comes back and it can react with water to produce HPO4 2-, and then this one also reacts to form this. But these are actually double barbed arrows, meaning they can go back and forth. They are not as strong as the first reaction. So Lewis acids and bases is a completely different type of explanation. So this one is the only one that does not assume the use of hydrogen. So a Lewis atom is a Lewis acid is an atom, an ion, or a molecule that accepts an electron pair. Now, technically, we're going to think about this. If you're using hydrogen, that can also accept electron pair. But if we look at BF3, boron does not have any more electrons. So if it wants to bond with another fluorine, or in this case fluoride because it's charged, it's going to have to get those electrons from fluorine. So here we have fluorine, but then we actually have fluoride because it has 8 electrons. So these 2 electrons are going to go to this empty space to form the BF4, and it's going to share the whole pair of electrons with the boron. So when it does that, it's acting as, boron is acting as a Lewis acid, and the fluorine is acting as a Lewis base. It's donating that pair. So this is the broadest definition of all of the acid bases. It's probably the one that most people find difficult to understand because it is so broad. But this will be something you might use in organic chemistry more often because you have to expand your definitions. So a Lewis acid-base reaction is where we're forming covalent bonds in the electron pair donor and electron pair acceptor. So hydrogen can be involved because it actually has no electrons here. It's a proton, just a proton. So when it does bond here, it's going to have to be done by the nitrogen giving up the electrons. So the nitrogen actually is giving up the electrons to form that bond with the hydrogen. So both of those electrons are coming from the nitrogen. So that's when we see the bond form in the Lewis acid base way. So this is another example. Which is the Lewis acid and which is the Lewis base? Well, remember, boron has no electrons here, nitrogen does. So when they form this bond, both of these electrons are coming from nitrogen. So nitrogen is the electron pair donor, and boron is the electron pair acceptor. So which is which? So nitrogen would be the Lewis base and boron would be the Lewis acid. Conjugate acid bases. This is done with the Bronsted-Lowry acid base definition. So a Bronsted-Lowry acid is a proton donor, and a Bronsted-Lowry base is a proton acceptor. Conjugate base is a species that remains after the acid has given up a proton. So if I have H2SO4 and it gives up a proton, what's left? HSO4 minus. So this would be the acid, this would be the conjugate base. Conjugate acid is what remains after the base gains a proton. So if this were reacting, let's see a base here. So ammonia, and we add that to it, we get NH4 plus. So this is the base, this would be the conjugate acid. So there's one more hydrogen in the conjugate acid and there's one less hydrogen in the conjugate base. There's always a hydrogen difference between the two. And there's always a hydrogen, an acid conjugate base pair in every Bronsted-Lowry reaction. So here we have the acid. The acid is going to donate to the hydrogen, the water here. So when we left over, this is the acid. It's donating a proton to water, so this becomes the conjugate acid. What's left over from the acid becomes the conjugate base. And this was the base because it accepted the proton. So acid, base, conjugate acid. The stronger the acid, the weaker the conjugate base, because a conjugate base, if we say, okay, I have an acid, I think I drew that H2SO4, and it donates a proton, so what's left is HSO4 minus, right? So if this is the acid and this is the conjugate base, this is a strong acid. The conjugate base means I now have space to accept a hydrogen and act like a base where I did not before. So if it means it can accept a hydrogen, why would it want to? So this acid can't wait to get rid of its hydrogen. Why would it want to accept it back? So it's not going to be a very strong conjugate base. It's going to want to get rid of that hydrogen, and it does. So a strong acid or a strong base is always going to have a weaker conjugate. It allows us to judge which direction these reactions are going to go. And the reactions always move in the direction toward the weak acids and weak bases. So they're always going to move toward the weaker substances. Any species that can react as either an acid or a base is known as amphoteric. So amphoteric substances, water is the most common one that we talk about, but really it's anything that can act as an acid or a base. So any of these ones that we've been talking about, HSO4 minus, H2PO4 minus, those can act, and so HPO4 2 minus as well. It still has a hydrogen, but it still has room and it could accept another hydrogen as well. So they act as an acid or a base depending on the strength of the acid or base that it's reacting with.